Hi everyone, my name is Azadeh and I'm rheological scientist at UNESCO. Thank you for participating at 2020 SPE virtual conference. The topic of my presentation today is effects of viscoelastic properties of polymer melts on the in-trans flow pattern. Here you can see the outline of my presentation today, which is introduction, objectives, methods and experiments, results and discussions, and conclusion. In introduction section, I quickly talk about the elastic and viscous effects on polymer melt flow during a capillary extrusion process, namely corner vortex flow and elastic die swell. Viscoelastic polymer melts face both shear and extensional deformation during a capillary extrusion process. When a polymer melt enters into a small cross-section of a die from a large channel in the barrel, an interconverging flow is formed due to polymer melt's viscoelasticity as well as the abrupt contraction of the channel cross-section. This interconverging flow includes shear flow and extensional flow. It is well known that the elongational or extensional component of the flow, which happens at the entrance of the die, is expressing the elastic behavior of the polymeric fluid. Consequently, large elastic deformation energies are produced, either dissipated or stored in the melt, leading to an obvious entrance pressure drop. It is believed that pressure drop at the in-trans flow consists of two components of elastic pressure drop due to a stored elastic extension strain energy and viscous pressure drop due to viscous dissipation. The two pictures in this slide show the convergence flow patterns at the entrance to flat capillaries where melt passed through a sudden contraction of channel cross-section. At the entrance to a capillary from a large barrel, streamlines converge rapidly, and this generates a high degree of stretching along streamlines. As you can see in the picture on the left, for Newtonian fluids and for some polymer melts such as high-density polyethylene or linear low-density polyethylene, all streamlines stretch in a regular way from the barrel into the capillary die. As you can see in the picture on the right, on the other hand, for non-Newtonian fluids, specifically for some certain polymers such as low-density polyethylene, there might be prominent stationary vortices and vortex flow at the sharp corner of the die entrance. These corner vortices produce unstable flow patterns, and in severe cases, it can cause the distortion of the extruded melt. This is even more severe for polymers with high melt elastic behavior, for example, polymers with compact long chain branch structure or polymers with broader molecular weight distribution. Generally speaking, polymers' molecular structure has effect on the polymer's melt elasticity. For example, polymers with linear molecular structure have weaker melt strength and melt elasticity than branch polymers. The reason is that linear chains slide by without getting entangled during extensional deformation at the die entrance. However, the long chain branches in polymers' molecular structure entangle while flowing through a capillary die, which results in having higher melt elasticity. Moreover, other kinds of undesired flow instability and extruded distortion, such as elastic die swell at the exit of a die, can happen during the capillary extrusion process due to elastic nature of polymeric fluids. For the origin of the die swell of viscoelastic polymers, there have been various interpretations such as normal stress effect, elastic energy effect, orientation effect, or memory effect. We at this work focused on two of these sources. One of the sources that originates elastic die swell is the shear flow induced orientation inside the die, which mainly depends on the shear rate that polymer faces inside the capillary. Shearing in the die produces a moderate degree of axial orientation, and this will lead to a certain degree of extruded swell. The other main sources that originates elastic die swell is the stretching at the entrance of the die. This depends primarily on the entrance streamline convergence as well as the recoverable elastic extensional deformation energy stored in the polymer melt. If these stresses cannot be relaxed, the corresponding elastic deformation will be recovered after fluid leaves the die, leading to extruded swell. The die swell, which originates from entrance extension, is more severe for shorter capillary dies because long residence time inside a long capillary can release some of the stored elastic strain energy and reduce the intensity of the die swell. But why is this subject important? Analyzing the elastic properties and predicting the entrance flow pattern of viscoelastic polymer melts is important for designing dies and flow systems in process simulation purposes. Another benefit is for extrusion process control. This is even more essential for the processes that are involved with a stretching of polymer melt, such as tube extrusion or extrusion blow molding. Moreover, unstable flow patterns at the corner of a die entrance may cause reduction of the process productivity due to the extra energy consumption for extruding the melt, as well as possibly producing defective materials. So this study also can help increasing process productivity. In this slide, I'm summarizing the objectives of this study. In this work, the relationships between various viscoelastic properties of the polymer melt, namely end correction, extensional stress, wall shear stress, and internally stored elastic pressure losses were investigated, while also understanding the effect of the die dimensions on these viscoelastic properties. Moreover, through analyzing the die swell behavior of the extrudates, a numerical approach was proposed to quantitatively predict the intensity of the corner vortices in the entrance flow. In the next section, I'll talk about the methods and experiments regarding to capillary dies and material, capillary rheometer and calculations, and die swell measurements. The base polymer evaluated in this study was LDPE with the melt mass flow rate of 1 gram per 10 minutes at the ASTM D1238 testing condition. In order to investigate the effect of die geometries on the elastic properties and entrance flow pattern of the polymer melt, 3 sets of capillary dies with different diameters of 1 mm, 2 mm, and 3 mm were selected. The length to diameter ratios of the dies at a given diameter were 4, 10, and 20. In order to maximize the elastic response of polymer melts during capillary extrusion, the entrance angle of 180 degrees or flat die was selected for all the capillary dies. The rheological characterization of the materials were carried out using a Dynisco LCR 7001 capillary rheometer. Dynisco LabCars software was used to measure various viscoelastic properties of the polymer melt. The entrance pressure drop was determined using Bagley method. Correspondingly, the Bagley corrected shear stress at wall was calculated by subtracting the entrance pressure from the driving pressure. Also, the end correction parameter was calculated for a given die with a specific dimension. The end correction represents the length of the capillary divided by diameter, for which fully developed flow would give the extra entrance pressure drop. Moreover, the extensional stress, extensional rate, and extensional viscosity were calculated using the data of entrance pressure drop and Coxwell equations. Finally, the elastic pressure losses was calculated using Coxwell method. Coxwell in his work showed that these elastic pressure losses are the factor of the channel cross-section contraction ratio, which is barrel diameter to die diameter ratio. In order to analyze the elastic die swell behavior of the materials, the diameter of the extrudates were measured using a laser scanning gauge and laser beam. This accessory element, which was installed behind the capillary die exit, had the light source of 800 nanometer laser. Finally, the die swell ratio was calculated by dividing extruded diameter to the capillary die diameter. In the next section, I'll talk about the results and discussions, and the titles are correlation between end correction and extensional stress to shear stress ratio, extensional deformation flow curves, die swell analysis, and entrance vortex flow analysis. This figure shows the relationship between the two dimensionless parameters of end correction and extensional stress to shear stress ratio for LDPE melts flowing through dies with different diameters. Both extensional stress and end correction parameter are rheological significance of entrance pressure drop. These rheological parameters express the elastic behavior of a given polymer melt, and therefore some kind of correlations must exist between them. As it can be seen from this figure, the end correction parameter increased as a linear function of extensional stress to shear stress ratio with the slope of nearly close to 1. Moreover, the elastic characteristics of LDPE melt were reduced with increasing the die diameter. The reason is that the contraction ratio, which is barrel diameter to die diameter ratio, is smaller for bigger diameter dies, leading to the reduction of entrance pressure drop and these elastic properties. The results from this figure confirm further that extruding through a bigger diameter die favors extensional flow deformation of polymer melts due to the existence of high resistance to the shear flow deformation by using bigger diameter dies. White was a researcher that studied on polymer melt flow pattern through capillary extrusion process. He and his colleagues in their work hypothesized that vortex flow occurs when the ratio of extensional stress to shear stress is high, or in other words, that happens when the resistance to stretching is larger than resistance to shearing. In our work, as you can see, this condition happened for LDPE melts when the polymer melt was flowing through dies with diameter of 1 mm and 2 mm. This figure shows the graph of extensional viscosity versus extensional rate for LDPE melts flowing through dies with various diameters. As it can be seen from the graph, LDPE melts showed extension stiffening behavior while extruding through the dies with 1 mm and 2 mm diameters. By flowing through the 3 mm die, however, the extensional viscosity of the melt was less dependent to the extensional rate. The reason is that the long chain branches of LDPE melts entangle more while flowing through a smaller capillary die, which results in having higher melt strengths. As the die diameter increases, however, the branch chains slide past one another and entangle less, which causes reduction of the extensional viscosity. Binding was a researcher who studied polymer melt flow at the entrance of a capillary in his work and assumed that the flow pattern with the lowest energy dissipation dominates the fluid deformation at the die entrance. He further concluded that sharp vortices happen for materials with extension stiffening behavior. In our work, extension stiffening behavior was observed for LDPE melts extruding through flat capillaries with diameter of 1 mm and 2 mm, which can intensify the occurrence of flow instability and corner vortices at the entrance of those dies. In order to predict the entrance flow pattern for various dyes, the extruded swell behavior of LDPE melts was analyzed under the test condition. The figure in this slide shows the dye swell ratio versus entrance elastic pressure drop for LDPE melts flowing through dyes with different diameters. The length to diameter ratio of all the dyes were constant at 4 in order to minimize the relaxation of entrance stored strain energy inside the dye. As I discussed in previous slides, one of the main sources of elastic dye swell in a capillary extrusion process depends on the amount of recoverable elastic energy stored in the melt at the dye entrance region flow. As it can be seen, the dye swell increased with increasing of the entrance elastic pressure as a power law function. The reason is that the elastic pressure drop results from extensional deformation in the entry flow, leading to the recovery of the stored elastic energy upon exiting from a short capillary. As it can be seen, the power law relation between dye swell ratio and entrance elastic pressure drop is stronger for 3 mm dye. As the diameter of the dye reduces, however, this dependency lessens and the plot levels off after a certain amount of extension. This phenomenon could be explained by the possible occurrence of sharp corner vortices at the entrance flow, which relax some of the recoverable elastic deformation energy and as a result reducing dye swell ratio intensity. We assume that the longer vortex flow lengths at the dye entrance sharp corners, the more relaxation of stored elastic deformation energy in the melt, which means there are less elastic deformation energy available to recover. In order to quantify the magnitude of the vortices flow patterns for various dyes, the slope of the power law function of the graph of dye swell ratio versus entrance elastic pressure drop was selected and named as the inverse of vortex index, as you can see in the equation in this slide. In this equation, C is a constant parameter relates to the polymer melt elasticity, and V is the vortex index. V or vortex index is a dimensionless number and represents the intensity of the corner vortices in the entrance flow. We are assuming that polymers with higher vortex index parameter have less dependency of dye swell ratio to the entrance elastic pressure drop, because, as I said before, vortex flow enhances relaxation of recoverable elastic deformation energy, leading to weakening of extruded swell. The vortex index parameter at each point of the graph of dye swell ratio versus entrance elastic pressure drop was determined by calculating the derivation of the log-log plot. The figure in this slide shows the graph of vortex index, which I explained how to calculate it in the previous slide, versus extensional stress to shear stress ratio for LDPE melts flowing through dyes with different diameters. As it can be seen, the length of the vortex index increases sharply once the ratio of the extensional stress to shear stress is higher than about 2. This finding is inconsistent with White and his colleagues' hypothesis that vortices occur when the polymer melt flow shows more resistance to stretching rather than shearing. As it can be seen, the occurrence of vortex flow is more severe for the dyes with smaller diameters due to the sharper contraction ratio of the channel cross-section. Now, in the conclusion section, I highlight the important points from this work. So, in conclusion, we talked about convergence flow pattern of polymer melts, meaning that polymer melts face both shear and extensional deformation during capillary extrusion process. We also talked about various elastic effects on the polymer melt flow, namely entrance pressure drop, entrance extension, dye swell due to entrance stored elastic energy, and entrance vortex flow. We at this work investigated the relationship between elastic properties of LDPE melts using dies with various diameters. We observed that N correction parameter increased as a linear function of extensional stress to shear stress ratio with a slope of nearly close to 1. Also, we observed tension stiffening behavior for LDPE melts while extruding through dies with diameters of 1 mm and 2 mm. We further observed weakening of elastic characteristics of LDPE melts with increasing the die diameter. Moreover, by analyzing the die swell behavior of the extrudates, we proposed a numerical approach to quantify the intensity of the corner vortices at the entrance flow. Finally, we concluded that vortex flow intensity increases sharply once the extensional stress to shear stress ratio is higher than about 2. The proposed model in this work, which predicts the entrance vortex flow intensity, is beneficial for numerical simulation of viscoelastic polymers as well as designing of various flow systems. Eventually, this helps improving the efficiency of capillary extrusion process and developing plastic products with higher final quality. With that, I would like to say thank you for your attention and listening to my presentation.